Hello everyone, welcome to this presentation on the evaluation of the operating savings of fossil energy and emissions based on photovoltaic thermal panels and RESHeat storage. This is a collaborative work between Krakow University of Technology and Brno University of Technology. Let's have a look at the RESHeat system. Within the context of a building, the RESHeat system features sun tracking solar collectors, thermal collectors, photovoltaic thermal collectors, as well as two heat storage tanks with sensible heat storage. It has also heat pumps, management controller, and management system. Of course, also an inverter and combination with interfaces to the central grid. The new technology involves photovoltaic modules with added cooling equipment, which produces a combined photovoltaic thermal module, and an additional improvement for increased power generation involves sun tracking, which increases the exposure of the panels to the solar irradiation. The excess heat from the PVT panels and the solar thermal collectors is used to charge the underground heat storage tanks and for ground heat regeneration. The latter takes place via tank 1, which is not insulated, so in the summer it transfers heat to the ground, and in the winter it transfers heat back from the ground to the tank for the usage by the heat pump. The preliminary tests of the system show that it can cover up to 90% of the building heating demands, and this is used in the current demonstration setup to check the feasibility of larger scale operation. It is possible to also estimate the potential emission reduction, at least for greenhouse gases. If we take a typical household annual consumption of power as 10 megawatt hours per year, and if we take also the average greenhouse gas intensity for Germany and Poland as 0.35 and 0.736 kilograms of carbon dioxide per kilowatt hour, for the 90% substitution offered by RESHeat installations, the savings of greenhouse gas emissions amounts to 2,900 roughly for Germany kilograms of CO2 per year, and for Poland to slightly above 6,300. And if we take this on a percentage basis, the reduction for Germany is 83%, for Poland conditions is 86%. In summary, the RESHeat system is a fully renewable-based combined heat and power solution based on ground source heat regeneration and reuse. It is capable of achieving COP values of 4 and higher. It's been demonstrated in 2 different climatic zones, for locations in Poland and in Italy for residential buildings with different sizes. The target TRL value at the end of the project is 8, and the project is aiming to introduce the system to the market. In the current presentation, we are showing the opportunities to integrate RESHeat with industrial and regional total sites. Typically, a total site involves several processes, some of them industrial, others commercial or residential. This can also include hotels. The interactions on the site in terms of energy take place via steam mains or hot water mains and cooling utility mains. RESHeat system can be included into this interaction via the hot water mains. Let's have a look at one possible configuration, and this slide lists the assumptions. Typical RESHeat system outputs include that the hot water storage tank from the PVT panels will have a temperature of 65 degrees. The heat accumulator, which is connected to the underground, and for underground heat regeneration, has the temperature of 35 degrees. So this is also available as a hot water temperature level, and the ground temperature is assumed to vary between 10 and 35 degrees. So 4 processes are considered for a typical configuration in a residential or urban setting: 2 industrial processes of small industry, a hotel and a residential area. The current case study data has been derived from published works. This is the table listing the data for the industrial processes, process A and process B. Process A has 5 process streams. Process streams A1 and A2 are hot process streams, which can be seen by the temperatures running from 150 down to 80, 170 down to 80, and the other 3 process streams are cold streams, which means they require process heating. In a similar way is described process B. For each process stream, besides the temperature, we have also the heat load. And here are the hotel and residential area streams. Hotel has several process streams: soapy water, condensate, bath stream, laundry stream, swimming pool water, cooking, and space heating. Process D is the residential area, only with cold streams requiring heating of baths and space heating. The initial pinch analysis of the 4 processes generates the grand composite curves, and they show some heating and cooling demands resulting from the heat recovery. Processes A, C, and D have net heating demands, and process B has a net cooling demand for the entire site. But first, let's have a look at how we can apply the RESHeat system for each of these processes. For process A, we have a 300 kilowatt which can be directly covered by hot water supply from the RESHeat system, and another 6.5 megawatts which are at approximately 130 degrees, and they may need a heat pump if we would use RESHeat. Process B requires no utility heating. Instead, it requires utility cooling at relatively high temperatures at 250 degrees and at about 30-35 degrees. With respect to the RESHeat temperature levels, it can generate hot water at the temperature level of the photovoltaic thermal heat storage and at the solar collector storage at 65 and at 35 degrees Celsius. Concerning process C, it has a requirement for approximately 513 kilowatts, which can directly be supplied by the RESHeat system using the solar collector tank, and 478 kilowatts can be additionally upgraded by a heat pump from the PVT temperature level. Concerning process D, it needs only utility heating. One level is the lower level, 741 kilowatts at 35 degrees, and additional 250 kilowatts have to be served by the 65 degrees hot water circuit. Both of these are feasible with the RESHeat system. Combining all four processes produce the total site profiles, which are the heat source and heat sink profiles. This slide shows how the total site integration would be performed, only including the industrial processes without RESHeat integration. Here we have the low pressure steam demand and the low pressure steam generation, and the rest of the heat would be disposed to cooling water. This results in a cooling water demand of nearly 3.6 megawatts and a net low pressure steam deficit of about 8.2 megawatts. Adding the RESHeat system adds two more utility levels for the 65 and the 35 degrees hot water. This allows saving another 433 and 1367 kilowatts via heat recovery between the processes. This immediately results in 85% reduction of the utility heating demand. Additionally, the steam users initially need 8,939 kilowatts of low pressure steam, but from those, about 1,367 kilowatts and 433 can be covered by the heat recovery, plus 729 kilowatts comes from site heat sources. So the final boiler requirement comes down to 6,410 kilowatts, which is 22% reduction from the initial steam demand. While the RESHeat system does take some investment, the return on investment is pretty quick. This slide shows the estimations for the net present value compared to currently available installations for electricity prices in August 2022, and one can clearly see that the cash flow becomes positive at year 4 to 6, which is pretty fast for energy installations. However, since the electricity and fuel prices, especially gas, are expected to grow, um, here is an extrapolation and a projection for the winter 22-23 for Polish conditions, and one can see that RESHeat installations become cash flow positive already a third to fourth year after installation. Here are the unique value propositions offered by this type of arrangement. It can serve up to 90% of the heating needs in the residential context, and it generates power at a higher efficiency than usual simple photovoltaic panels. This type of system provides high energy independence, high degree of security of energy supply, and it is environmentally friendly. Moreover, with respect to the current energy prices, it yields expected positive net present value after year 4 of installing an operation. For more information, you can visit the RESHeat website. We have also created a YouTube channel for more visual and contextualized presentation of the demonstrations. So to conclude, the RESHeat system offers a flexible combined heat and power generation. The heat is provided at two temperature levels for hot water, 65 and 35 degrees Celsius. It can cover up to 90% of the heating needs and plus power generation. We have seen in this presentation that RESHeat can be also integrated into local total sites, including small industry, and the case study demonstrates a significant reduction potential for utility heating of up to 22% and utility cooling up to 85%. And the project demonstration further has steps for evaluation of the RESHeat economy in detail, contextualized to different application regions. And also footprint and eco-cost benefit analysis will be further performed. The RESHeat system itself is described in detail with all its fundamental models and equations in this book as well. We would like to acknowledge the funding from the RESHeat project via the Horizon 2020 program for research and innovation under the grant agreement concluded with the program. So thank you for your attention, and I'm looking forward to the discussion.